Welcome to an exploration of one of the most fascinating phenomena in nanoscience, how tiny clusters of metal atoms can behave like giant atoms. Imagine a cluster of just a few dozen metal atoms that suddenly starts behaving like a single giant atom with its own electron shells. This is the world of metallic nanoclusters. Let's start by understanding what metallic nanoclusters actually are and why they're so special. Metallic nanoclusters are tiny assemblies containing anywhere from 2 to about 1,000 metal atoms, sitting at the boundary between individual atoms and bulk materials. Their size ranges from about half a nanometer to 3 nanometers in diameter, which is incredibly small, about 100,000 times smaller than the width of a human hair. Here we see the progression from a single atom to a small cluster of a few atoms, to a nanocluster containing dozens of atoms. Common metals used for these clusters include gold, silver, aluminum, and sodium, each exhibiting unique electronic properties at the nanoscale. Now let's explore why these clusters behave like giant atoms with shell structure. Remember how atoms have electron shells that fill up with specific numbers of electrons? 2 in the first shell, 8 in the second, 18 in the third, and so on. In regular atoms, electrons occupy discrete shells with these magic numbers due to quantum mechanics. Amazingly, metallic nanoclusters show similar magic numbers, but for the total number of delocalized electrons in the entire cluster. The magic numbers for nanoclusters are 2, 8, 18, 20, 34, 40, 58, and so on. Clusters with these exact numbers of delocalized electrons are exceptionally stable. The key to understanding this behavior lies in the Jellium model, a simplified theoretical framework. The Jellium model assumes that valence electrons move freely in an average potential created by all the positive metal ion cores smeared into a uniform background. Imagine a box filled with a uniform positive charge representing the ion cores, with electrons moving freely within this background like particles in a quantum box. Instead of the complex 1 over r potential of individual ions, we replace it with a constant average potential V0. For spherical clusters, this simplifies to a three-dimensional harmonic oscillator problem, which we can solve exactly using quantum mechanics. The potential becomes 1/2 m omega squared, r squared, where omega is the oscillator frequency and r is the distance from the cluster center. Now let's see how energy levels emerge and how electrons fill these shells. The energy levels are given by h bar omega times the quantity 2n plus L plus 3/2, where n is the radial quantum number and L is the angular momentum quantum number. The energy levels split into shells labeled by quantum numbers. The 1s shell holds 2 electrons, 1p holds 6, 1d holds 10, and so on. When we add up the electrons to fill these shells sequentially, we get shell closures at exactly those magic numbers we mentioned: 2, 8, 18, 20, 34, 40, and 58. For example, 2 plus 6 equals 8 electrons for the first 2 shells, and 2 plus 6 plus 10 equals 18 for the first 3 shells. How do we know this theory is correct? The evidence comes from beautiful experiments. When scientists create beams of metal nanoclusters and measure their abundance using mass spectrometry, they see dramatic intensity peaks at specific sizes. The mass spectra show huge peaks at the magic numbers like 8, 20, 40, and 58, indicating these clusters are much more abundant and stable than their neighbors. Sodium clusters are particularly striking examples. Sodium 8, sodium 20, and sodium 40 are exceptionally stable and appear as prominent peaks in experiments. But why exactly are these magic number clusters so special and stable? At shell closures, there's a large energy gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, similar to noble gases in chemistry. This gap, delta E gap, equals the energy of the lowest unoccupied orbital minus the energy of the highest occupied orbital. A large HOMO-LUMO gap means it takes a lot of energy to add or remove an electron, making the cluster chemically inert and thermodynamically stable. For sodium-20, this gap is about 1.5 electron volts, which is substantial and explains why this cluster resists chemical reactions. Let's do some real physics and estimate the oscillator frequency for a typical nanocluster. The oscillator frequency omega equals the square root of the spring constant K divided by the effective mass. For a gas of electrons confined in a sphere of radius r, we can estimate omega from the electron density. The energy scale, h bar omega, is approximately h bar squared over electron mass times r squared times n to the 1/3 power. The cluster radius r is approximately r sub s times n to the 1/3, where r sub s is the Wigner-Seitz radius, typically 2 to 4 angstroms for metals. For sodium-20, with radius about 0.7 nanometers, let's calculate the energy scale. Plugging in h bar equals 1.05 times 10 to the minus 34 joule seconds, electron mass 9.1 times 10 to the minus 31 kilograms, and r equals 0.7 nanometers, we get approximately 0.7 electron volts. This gives us about 0.7 electron volts, which is remarkably close to experimental measurements, validating our simple model. These electronic shells give rise to fascinating optical properties, particularly plasmon resonances. A plasmon is a collective oscillation of the entire electron cloud against the positive ionic background, like a vibrating jelly. When light hits the cluster, it can displace the electron cloud relative to the positive background, creating a restoring force in oscillation. The plasma frequency is given by omega p equals the square root of Ne squared over electron mass times epsilon 0, where N is the electron density. Gold nanoclusters show strong plasmon absorption in the visible range, which is why they appear brilliantly colored, unlike bulk gold. As the cluster size changes, the plasmon frequency shifts due to quantum confinement, producing different colors for different size clusters. Magic number clusters exhibit enhanced properties that make them technologically important. Magic number clusters resist oxidation and chemical reactions due to their large HOMO-LUMO gaps, making them stable in harsh environments. Their catalytic activity can be precisely tuned by selecting specific cluster sizes, with some sizes being extraordinarily active catalysts. This graph shows how catalytic activity varies dramatically with cluster size, with peaks often occurring at or near magic numbers. Magic number clusters show enhanced third-order optical nonlinearities, making them useful for ultra-fast optical switching and signal processing. Some metallic nanoclusters even exhibit superconductivity, with properties that oscillate with size. Aluminum nanoclusters can exhibit superconductivity, but interestingly, it disappears below a critical cluster size due to quantum size effects. The BCS superconducting gap delta equals 1.764 times Boltzmann's constant times the critical temperature. For superconductivity to exist, the electronic level spacing delta must be smaller than the superconducting gap, otherwise pairing cannot occur. The level spacing delta is approximately the Fermi energy divided by the number of electrons, and this must be less than the BCS gap. For aluminum, the critical size below which superconductivity disappears is about 10 to 20 nanometers, corresponding to a few thousand atoms. The critical number of atoms is roughly Fermi energy divided by the BCS gap, giving about 1,000 to 10,000 atoms for typical superconductors. You might be wondering, how do scientists actually create these precisely sized nanoclusters? One method is laser ablation, where intense laser pulses vaporize a metal target, creating a plume of atoms that condense into clusters. The laser creates a plasma that rapidly cools, and atoms aggregate into clusters of various sizes that can then be separated. Another method is chemical synthesis, where metal ions are reduced in solution and stabilized by protective ligands that control the cluster size. A third method uses ion beams, where clusters are formed, ionized, and then size selected using a mass spectrometer before deposition. Let's look at a concrete example, the famous Gold-20 cluster, which has been extensively studied. Gold-20 has a pyramidal tetrahedral structure with 20 gold atoms arranged in a highly symmetric configuration. It has a HOMO-LUMO gap of 1.8 electron volts, making it exceptionally stable chemically. Its diameter is approximately 0.7 nanometers, barely 3 times the size of a single gold atom. Gold-20 is remarkably effective at catalyzing carbon monoxide oxidation at room temperature, unlike bulk gold, which is chemically inert. Let's directly compare a normal atom with a superatom to see the parallels. On the left, a normal atom with electrons orbiting a nucleus. On the right, a superatom with delocalized electrons orbiting the entire cluster of metal atoms. Atoms fill shells following the Aufbau principle. 1's 2, 2's 2, 2p6, and so on, based on the atomic number Z. Superatoms fill shells similarly but with the Jellium ordering, 1's 2, 1p6, 1d10, based on the total number of delocalized electrons. In heavier elements, spin-orbit coupling modifies the simple Jellium picture. Spin-orbit coupling breaks the degeneracy of electronic levels that have the same principal and angular quantum numbers. The energy now depends on the total angular momentum quantum number J, with an additional term proportional to L.S, the spin-orbit coupling. Gold and platinum clusters show particularly strong spin-orbit effects due to the large nuclear charge, leading to modified magic numbers. With spin-orbit coupling, new magic numbers emerge, 14, 38, 54, which differ from the simple Jellium predictions. Many properties oscillate as we vary the cluster size, creating a fingerprint of shell structure. Properties like ionization potential, electron affinity, and reactivity oscillate with cluster size, reflecting the filling and opening of electronic shells. Ionization potential reaches local maxima at magic numbers where shells are closed, requiring more energy to remove an electron. Chemical reactivity shows minima at magic numbers because these clusters are most stable and least likely to react. The ionization potential varies roughly as the bulk value plus alpha over n to the 1/3 with oscillations superimposed. Even the melting behavior of nanoclusters shows quantum effects tied to shell structure. The melting point of nanoclusters depends dramatically on size, generally decreasing for smaller clusters but with oscillations. This graph shows how melting temperature generally increases with cluster size, approaching the bulk value but with notable irregularities at magic numbers. Magic number clusters show enhanced thermal stability and can withstand higher temperatures before melting compared to neighboring sizes. The melting temperature follows roughly Tm bulk times 1 minus a correction term involving surface energy gamma and cluster radius r. These remarkable properties make metallic nanoclusters valuable for cutting-edge technologies. In catalysis, size-selected nanoclusters provide unprecedented selectivity and efficiency, enabling new chemical processes. As sensors, they can detect specific molecules at concentrations as low as parts per billion due to their unique optical and electronic properties. The three main application areas are catalysis, sensing, and medicine, each exploiting different aspects of nanocluster physics. In medicine, gold nanoclusters serve as targeted drug delivery vehicles and imaging agents, accumulating specifically in tumor tissue. Looking to the future, metallic nanoclusters may play a role in quantum computing. The discrete, well-separated energy levels of magic number clusters could potentially encode quantum bits with long coherence times. A qubit state could be a superposition of the ground state and first excited state, psi equals alpha E0 plus beta E1. The main challenge is maintaining quantum coherence at practical temperatures, as thermal fluctuations can destroy the quantum state. Despite decades of research, many fascinating questions remain open. How exactly do protective ligands on the cluster surface modify the electronic structure in magic numbers? Can we reliably predict which cluster sizes will be most catalytically active for specific reactions? What new physics emerges in the intermediate size regime between small clusters and bulk materials? The three main regimes are small clusters, nanoparticles, and bulk materials, each with distinct properties and challenges.